Welcome to High Performance Computing Advanced Scientific Computing course, Lecture 12. In Lecture 12, we have Lattice, Boltzmann, and CFD application. We will talk about these new method in contrast to the traditional method in the computational flight dynamic, and it's relevant to high performance computing. Based on the outline of the course, it is Lecture 12, and this year, as we said, is special for the CFD. In the beginning, let's have a review of the Lecture 11. In the Lecture 11, we had introduction to application of the deep sequential model for computational flight dynamics, and we looked at the advantage of the recurrent neural network, especially long short-term memory, LSTM, and its variant like GRU, gated recurrent unit. And we saw its capability could be interesting to use in the turbulent flow as an unsolved problem in the fluid dynamic. We talked how we need to create data with time series and in sequential from fluid dynamic, and then use it in this type of the model. Then we had discussion about the experiment we used to test this model. We especially focused on the LSTM variants and GRU, and we had talked about the Lagrangian framework, which make possible to use data from the turbulence flow in the time series manner, and then train this type of the model and see its prediction. We had indeed practical example from our recent study. We used the data from strain turbulent flow, which is created in the laboratory experiment, and then without any post-processing of the data, we use the data in the raw form in the Lagrangian framework time series, and we trained the LSTM and GRU model with the data that could be able to predict the velocity component individually. That means when we had the measurement for two-dimensional in x and y direction, we are able to make a prediction for x and y separately. And also, if we have the third dimension, we can make this prediction for it. And this make the model is flexible. We presented the result of the prediction was successful, which is show how the LSTM variants are applicable in this area, and it's good step in the turbulent flow to be studied by the deep learning network like LSTM. Also, we took a look at its speed up in the high performance computing, and how when we use the GPU it gets faster. To present application of these fundamental model, we used it to predict the wind speed, which is applicable in the energy industry, to predict the wind power and make the smart grid able to respond to the demand of the power in the grid. And also this could be one of the advantage of this model to be used in the smart city and smart grid, which is currently follow in the many countries and also in the European zone countries. The lecture 11 was practically show the capability of the deep learning model like LSTM, that they are able to make some reliable prediction in the turbulent flow, which is one of the unsolved problem in the physics so far. Especially we mentioned that point focus on the large scale of the turbulent flow, which has not a theoretical understanding yet, and these type of models and approaches could help to understand this phenomena much more. Now let's come back to our lecture 12 regarding the lattice Boltzmann in the computational fluid dynamic. In this lecture, we will have two parts. Part one will have an introduction and the background about the lattice Boltzmann, the Boltzmann's equation, some condition that is required in this model, its advantage and disadvantage in contrast to the traditional CFD and its application. Then in the second part, we will try to have some methodology discussion, how the modeling with the particle flow and the particle tracking, then its application for turbulent flow, and some example from the large eddy simulation, which is relevant to lattice Boltzmann. Then there is the part one of the lecture. Regarding the lattice Boltzmann, let's investigate the first discussion we had in the introduction about the CFD. We said in the computational fluid dynamics we have three methods usually used based on the fluid studies and governing laws. It's experiments, analytical solution, and numerical solution. We counted the advantage and disadvantage of these method. For example, experiment is limited because of the size and also about the cost. We are not able to make the experiment for every scaling. However, the experiment could be validation for the numerical approach. For the analytical solution, there are not too many analytical solutions for many problems, so usually it's only for the simplified form and linear, and also it's so costly to solve the analytical solution. However, it's present general solution for the equation that is applicable in many other methods. But regarding the numerical solution, we said if we apply this appropriate method, it doesn't have any limitation. It could be to reduce the cost and operation and the computational cost. We can apply the numerical method for complex problem, especially with the geometry, and we can validate it before the application. There are two main items it's required to be prepared for the numerical solution, to specify the boundary condition, initial condition, and also the computing power, which this part is relevant to HPC. Then when we use the numerical approach, we need to have the enough computer power to solve the problem. Then we look when we look on this approach also about the numerical solution for the turbulent flow. Also, there are some limit. We said when we use the DNS provide exact one, but it's so costly. LES and RANS also has some other limit. We said RANS, for example, in some example, when we have some geometry change is doesn't recognized by the RANS in the solution, and LES also costly, and we are dealing with the eddy scale, which we said it's relevant to hypothesis of the turbulent flow by K41. So when we look on the available perspectives, each one has some limit. Then it seems that's why we talked in the previous lecture. The deep learning, this could be another technique to be used in the fluid dynamic and turbulent flow especially. And now we want to talk about the lattice Boltzmann, how it could be applicable in this area and helping. First, before we start about the Boltzmann equation, we need to have a description of the scale or scaloscope. There are three scaloscopes when we're studying the physics of the domain. for example, the fluid dynamic, the microscopic one, which is related to continuous domain, the microscopic one, which is non-continuous and based on the particle. In the microscopic approach, we are following the particle behavior in the flow, and in the mesoscopic, it's based on the statistic of the particles, which we can say it's collecting information from the group of the particle. This different description level has a different input. For example, for the microscopic, we need effective parameter. For the microscopic one, we need individual fluctuation. And for the mesoscopic one, as we said, we need average fluctuation. So we take the group information of the data. The mesoscopic scale located between the microscopic and microscopic scale, which this scale definition led to Lattice Boltzmann approach, and we will talk in the next slide about it, how it's led to this one. Then that means about the turbulent flow, as a reminder, we said the statistic in the turbulent flow is applicable based off the theory of the statistics. And then there is some concepts that are relevant to turbulent flow and are applicable based on the mesoscopic scale. Now, according to these three scale scope that we mentioned in the previous slide, let's look at their detail. The microscopic scope, it's based on the continuity. Indeed, in this scope, the molecule main free path should be too larger than a smallest flow length scale. And there is a Knudsen number which make based on its range, the flow has a different behavior. For example, when the Knudsen between 0.001 and 0.01, it's called a slip flow, and it's this condition used in the Navier-Stokes equation. However, when we have the microscopic scope, we are dealing with partial differential equations, and we have limitation to solving this type of the equation, especially when we use the CFD for three-dimensional, for example, problem. It's so costly. This is rather than the turbulent issue that we have. Regarding the discretization also, it's lead to error in the solution because we're calculating H-node properties and we collecting the information. So you imagine when we have a very, very small error for each point or each node, and then we're collecting all of these nodes, this gathering of the error will lead to larger error in the solution. So this is the another issue also we have. Regarding the mesh generation also, this is another problem in the CFD. Usually in the CFD problem, we are most of the time we say 50% of the work spent on the meshing of the problem, and also there is a limitation about the meshing for some specific amount like porous medium. So these some limitation and obstacle make the microscopic scope is limited to some application, and we are looking to some other approach and scope to deal with the kind of the problem that's not covered with the microscopic scope. When we look in the microscopic scope, it's only follow the particle, which means we are studying the particle properties. It has a particle governing motion. So when we have these concept, then we can get the whole flow motion. Then firstly we're studying the particle, and then we accept to get the whole flow motion. We are studying the dynamic of the molecule. For example, the Newton's second law for single particle used to explain the particle. The solution has a high accuracy when we use the microscopic approach. But you imagine when we're using the microscopic approach, we are doing the calculation for every secant temperature. The computation to cost, especially when we have actual sense problem and large problem. It's because of the computing is limited for few million particle and short period. Then, because of the computation, because of the number of the particle, we are dealing with computation. Also, when we have time period of the problem, we are not able to make this computation for the long period. So there is two limitation in this approach. However, because we are studying the individual particle, it's easy understanding and easy programming because we are writing the program for a single particle. However, the cost and the limit that we mentioned in this area, it make it difficult to apply it for the large and real size problems. Now let's look at the mesoscopic scale and how it's led to lattice Boltzmann. It's similar to microscopic one, however, we are taking average of the information, not the individual. Instead of the single particle, we are look at the statistic view. It's possible to use it for the long period and large data set. Indeed, the goal is understanding the average of the properties and probability distribution. The probability distribution function in this regard, it's so applicable because we're studying the statistics. Probability of finding a particle at location R at time t with momentum p. So this is the main, we can say, statement in the mesoscopy one. And with this probability finding, we are using the average of the statistics. The probability particle distribution function is the response to this question, and based of the probability particle distribution function, the lattice Boltzmann method basically is created, and we will see how it works. To see where the lattice Boltzmann method came, let's look at the lattice gas automata. Indeed, the lattice Boltzmann method is direct descendant of the earlier model of the lattice gas automata. It's called LGA. Is a type of the cellular automaton used to simulate fluid flows. From the LGA, it is possible to derive the macroscopic Navier-Stokes equation, which is the main concept, the fluid dynamic. Interest in the LGA method is leveled off in early 1990, based off the available background. This model comprises a lattice where the sites on the lattice can take a certain number of different states. In lattice gas, the various states are particles with certain velocities. Evolution of the simulation is done in discrete time steps. After each time step, the state at a given site can be determined by the state of the site itself and neighboring site before the time step. In the propagation step, each particle can move to a neighboring site determined by the velocity that particle had. So regarding the particle when simulated on this model in the LGA, it's based off the collision, which means when two particles collide to each other. In the collision step, collision rules are used to determine what happens if multiple particles reach the same site. These collision rules are required to maintain mass conservation and conserve the total momentum. Therefore, based off these two conservation, this model is working, and these led to lattice Boltzmann method. However, this model also has some modern and advanced approaches. It's used, for example, some LGA variant like bio-LGCA are still widely used in the model collective migration in the biology. In this slide, we have an example of the one of the model in the LGA approach. It's called HHP. It's proposed in 1973, and as you can see, it has a four particle neighbor. Indeed, the grid is two-dimensional, and each node in the grid has four neighbors, which they are labeled C1, C2, C3, and C4. About the motion and collision that's happening between the particle, for each time step, each particle is moved forward one step in the direction of its velocity, as you can see in this figure here in this slide. When two or more particles meet at the same node after a time step, a collision occurs. So this is the model that's simulating the collision. To conserve mass and momentum, the number of particles and the total velocity of all particles in a node must be the same before and after the collision. This statement must be met when we're simulating with this model. When three or four particles met in the same node, the only configuration that satisfies conservation of mass and momentum is the same configuration as before the collision, as you can see here in this slide. Thus, the collision between three or four particles cannot and does not result in the change of their configuration, and the particles stay on as if no collision occurred. So when we have the collision between three or four, it's same to no collision occurred. This is some assumption and condition required to be met on this model to be applicable. However, it is only two-dimensional model and we cannot use it for three-dimensional model, and this is one of the limits that is available in this modeling of the LGA. Now let's look on the HHP model advantage and disadvantage. One of the main issue that make this model could not be used on the fluid simulation, it's fail on the Navier-Stokes equation because HPC system fail to behave in accordance with the Navier-Stokes equation. So this make it useless on the fluid dynamic area. And not successful. However, there are other items and list of the disadvantage. For example, the microscopic state of the system is always changing. The microscopic quantity of the system can be found by averaging the microscopic quantities over space or time. However, due to the constant change in the microscopic state, there will always be a statistical noise in the microscopic quantities. So you can see many disadvantages. However, regarding the advantage also, it has some advantage, but the disadvantage and failing in the Navier-Stokes equations, it's make it useless in the fluid dynamic area. So we can see it is essential to take a serious step to make mesoscopic scale used in the fluid dynamic area. And now let's look at the another model. The another model from the LGA is FHP, which is proposed in 1986. This model was shown that by moving from a square lattice to a hexagonal lattice, the incompressible Navier-Stokes equation could be recovered due to the extra rotational invariance afforded by the hexagonal lattice. So here you can see in this figure, indeed we have 6 neighbors for each particle, as labeled from 6,1 to 6,3, 6,6. A hexagonal lattice allows 2 possible resolution for a head-on collision, which conserve both mass and momentum. This is what is different from the HP model we did. There is only one possible resolution, but here there are 2 possible. And you can see how specifying the velocity for lattice vector on the FHP model with C1 to C6, and they are presented on this figure. Uh, Now let's look at FHP model features. Indeed, we can say the idea of the lattice gas automata LGA is that if essential features of the real fluid are maintained on microscopic level, then the correct physical behavior will be reproduced at the macroscopic scale. Indeed, there are 2 basic assumptions in the LGA: local conservation of the particle at each time step and local conservation of the momentum at each time step, as we mentioned previously. Now in the FHP, it's characterized as follows: a hexagonal lattice of nodes. Each node has 6 neighbors, and cells can be occupied by at most 1 particle. All particle has the same mass. The evolution in time proceeds according to the predetermined update rules. Only particles of single node are involved in collision. When we look on the hexagonal lattice of HP model, we can see there are 6 velocity vectors in each node. And one of the disadvantage which is available on the FHP model, it's the noise. Indeed, this is a general problem when trying to recover macroscopic quantities from microscopic scope simulation, as the microscopic system is a subject to random fluctuation that disappear in the continuum limit. From FHP model also, it has a standard variation and also 2 other, FH2 and FH3. They are differ in the particle and additional collision. However, the principle is same. There are difference in the behavior in the different viscosity, for example. And so based off the its feature, it could be applicable, and there are many work has been done to simulate the fluid dynamic. For example, using the FHP, the standard one, to solving the problem from the Prisoner flow. It is possible and is available in the literature. However, because of the some limit, it seems these led to idea of the lattice Boltzmann, which is much more successful, and it's led to lattice Boltzmann equation. In the second part, we will talk about the lattice Boltzmann equation and how it came to the play, and its advantage and disadvantage, how it's relevant to high performance computing resources. It has some power than the traditional CFD. However, the lattice Boltzmann equation is still open research area, and there are many work using it to evaluating its capability and how using in the different range of the fluid dynamic like turbulent flow. Here we finished part 1 of the lecture 12 for the Lattice, Boltzmann and CFD application. Here there is a video presenting lattice gas simulation. I suggest you to watch it. It's presenting very interesting simulation, and indeed this is the capability of the lattice gas simulation. The link for the video is available in the references of the lecture. So we will continue in the part 2 of the lecture, and we will present the lattice-Boltzmann equation and with much more detail how we can use it for fluid dynamic studies. And there are some advantage of it for the computing regarding the high performance computing, and also for some application which are limited in the traditional CFD like porous media. The lattice Boltzmann present very good capability and solution. We will see them in the second part of the lecture. Thank you.